Okay, so what I want to do today is to cover, state and prove the Helmholtz theorem. It's a very useful theorem. It's a very profound result. It's not a very difficult result. But instead of discussing the various ideas that go into the proof while I'm proving the result, if we do so, we'll lose track of what's important. Let me begin with a few remarks, a few results, a few ideas that we're going to use in the proof separately, so that once we start the proof, it's a quick proof. It's a very powerful result. So I'm going to begin by looking at how I can approximate functions. Okay. So suppose you have a function f of x. There are many ways to approximate a function by series, by infinite series. You have certainly seen some of this in your calculus course. You have your Taylor expansion, your power series. One that we'll talk about today is power series. So how do I expand this? Well, any function, at least in a small region around a point, let's say in this case around x equals 0, can be expanded as some constant times another constant times x plus a2 x squared, so on and so forth. But that, and if you're trying to expand a function not about the origin, but about some other point, if it's about the origin, this is the only thing that will work. And you'll see why when I discuss the other possibility. What happens if you're trying to expand a function far away from the origin? And this would be of interest to us. We want to know how the function behaves as it approaches infinity. Well, then there may be other terms. Well, what terms? There could be inverse powers of x. So b1 times 1 over x plus b2 times 1 over x squared, and so on and so forth. Here, I don't need another constant. I can put a b0 because it's a constant. So here, a0, a1, b1, these are all constants that depend on f. So this will always work in a certain region. For example, why did I say certain region? For example, if I'm trying to expand f around the origin, I don't want any of these terms, because 1 over 0 would lead to be a problem. If I'm trying to find how a function behaves at infinity, and if the function is well defined, not infinite, I don't want any of these terms. So these constants can be 0 or different values depending on the function. Well, so these are constant that depends on f. So for every function, you have to use some technical means to come up with the values of the constant. I'll make that a little more clear. This is an important concept, not just for this theorem, but in general. So suppose I have a function in all space, okay? And we often do. So x, y, z. Consider initially, at any point r, consider a function, but it depends only on the distance. It doesn't depend on the angle. We'll do the other case shortly. So f depends only on r. And if you want to describe f by a power series, well, you have to be careful. You have to look at what region you're interested in. So one of the regions you could be interested in is the small area around the origin. This entire area. Okay, let me call that region 1. So in region 1, how would you power expand or write a series expansion for f? So I'm going to denote that by f with a subscript of 1. Note that it's a function of r. Okay? Well, there could be a constant that does no harm. There could be this series, a1 times r plus a2 times r squared plus. Now you might say, well, what about the other ones? What about the b terms? Well, what happens if we did this? At r equal to 0, we'll get infinity. So unless the function is not defined at r equals 0, these guys better be 0. Okay? So, and we won't consider functions at the moment that have infinity at a certain point. So in region 1, this is good. This is all we need. Okay? And I've arbitrarily chosen some distance. Okay? But it's a distance that includes the origin. Now, what about an intermediate region? Maybe I'm going to talk about this region. In this region, and let me call this region 2. R equals 0 is not included. R equals infinity is not included. And so, you would get a full expansion, a1r, a2r squared, all the way. This better be a convergent sequence, of course, plus b1 over r plus b2 over r squared. Because both r equals 0 and r equals infinity is not included, all of these terms are well defined. And once again, the coefficient should be such that this series can be summed, and indeed, we obtain f as a function of r in this region. Sort of getting a hang of what's going on. So what happens far away? This region includes r approaches infinity. Yeah? All the way. So f3. You can easily see what's going on. It could be a constant. As r approaches infinity, the function could have some value. But it can no longer have the terms proportional to r squared, r cubed, and so on and so forth, because as r approaches infinity, these values will go to infinity. Instead, it could have b1 over r, b2 over r squared, okay? All right, so that is another important point. Really, for us, this is the region that'll be most important. Okay, now I chose f to be a function only of r. What would happen if f is a function of r, theta, and phi? Well, let me write it just for region 3, because the same thing applies to all the other regions. So if you have f, r, theta, phi, again in region 3, same remarks apply here. You would have a0. It cannot be a function of r, because we're series expanding with respect to r. So a0 is a constant with respect to r, but it could be a function of theta and phi, plus b1 theta and phi over r, plus b2 theta and phi over r squared. This is what the series would look like. Similar remarks apply to f1 and f2, but what we need is faraway region. Okay? Now, we say if a0 exists, we say the function is of order unity, which means as r approaches infinity, you have a number. Suppose a0 doesn't exist, but b1 exists. Then we say the function is of order 1 over r. It goes to 0, But how fast does it go to 0? 1 over r. What about this one? Well, that goes to 0 faster, so we don't have to worry about that. Okay, it goes to 0 much faster. But the leading order term is how we describe the function. So if I say the function is of order 1 over r cubed, that means a0, b1, b2 is 0. The first non-zero term is b3. Okay. All right, so that is another fact we need. And you have seen in my previous lecture how we integrate over all sources to compute the electric field at a single point. So a description like that is important here as well. So suppose I have a function and I'm using the same symbols I'm about to use in the Helmholtz theorem. Suppose I have a function u and I have to calculate the function u at any point r. And let's say I want to, it is given by a certain formula. Okay. And I'm going to use the exact same formula that shows up in Helmholtz theorem so that you don't have to revisit it twice. I don't need a constant factor, but I'm going to throw it in because it shows up. You can consider this to be the definition of the function u. It is a function of the following quantity, d, which is a function of r prime, and integration is with respect to the prime coordinate. Now you might say, well, what is that? Well, you're familiar with this from the electric field, but there's a slight reversal. You're integrating over all space. The function u is to be evaluated at r. But to get u at r, you have to integrate this function over all r prime. This one is nothing more than r and r prime. So this quantity is also being integrated. The only place where r appears is over here. We want to know, is this well defined? Because we're integrating over all space, what happens if we get it to be infinite? Okay, there are a couple of things I want to know. I want to know how to approximate this guy, and I want to know how to approximate this guy. So, for a fixed r, I'm fixing this point, you see? So I'm going to call this r. I have to integrate over all r prime, and I worry about this when r prime becomes very large. I want to avoid infinities. So I'm drawing a diagram very different from the diagrams you've seen before, where the sources exist only in certain small regions. But here, it could be anywhere. So let's say this is r prime. And I want to approximate need to approximate one over the displacement vector and d of r prime for very large r prime. Now when I write just r, I mean the magnitude. Well, this guy is easy. Which one? Well, what does that mean? So I'm approximating it. There'll be other terms. Yeah? But this distance, so this is mine. This distance, if this is very far away, this looks very small. As I'm fond of saying, you don't see the Death Star very far away. Right? So this distance is practically this distance, for this being very large. Okay? So I can write this as 1 over r prime. There could be other terms. There are other terms, but they go faster. What I mean by that is there could be some constant times r prime squared plus r prime cubed, but these guys go faster to 0. I just want to make sure that the integral is well defined. If this one, when I put it into the integral, and I can integrate just fine, the other terms will not create a problem. So I'm only going to hang on to the leading order term. Okay? All right. What about this guy? Well, we don't know anything about the function d, except we know this is very far away, so this is region 3, huh? It is going to be some constant, which is a function of theta and phi, plus b1 theta and phi over r prime plus b2 theta phi over r prime squared. Now you wonder why I'm going to write this far out and not anything more. You will see where the problems lie and when will this quantity actually be integrable when you integrate over all space. Well, let's put this in. I have u of r, 1 over 4 pi. I didn't have to put that in, but that is for the Helmholtz theorem. And I have 1 over r prime and this guy. I'm going to hide the fact that all these constants depend on theta and phi. We just know it. Plus b1 over r prime plus b2 over r prime squared plus b3 over r prime cubed. And then the volume integral, obviously, I want to use a spherical coordinate system. So I will have r prime squared dr prime d theta prime d phi prime. Theta and phi are not very dangerous. I mean, you're just integrating over 0 to pi or 0 to 2 pi. It's the r that is going from 0 to infinity, or some value. No, we're in region 3. So some value r, let's just arbitrarily pick some distance very far away. Inside, it's a small compact area. Things will be well defined. We just want to know how it is defined for large r. Therefore, I'm going to focus only on integral of d of r prime over r prime over this d tau for large r prime, to make sure that they are finite. And so let's do this. I'll make this very clear. And so d r prime d tau prime. First of all, I'm not putting the 4 pi in, huh? That's something that, well, if you want to throw it in for completeness, we started it, so. And then I'm going to do, I don't even care about these two guys, 0 to pi, 0 to 2 pi. I'm interested in this r prime integral. So times this guy. Let's say some r not 0, far away, right? So I'm in region 3. So I'll pick some huge R, fixed. And then from here, all the way to infinity of, I'm going to carry this in here, and I have A0 over R prime plus B1 over R prime squared plus B2 over R prime cubed plus B3 over R prime to the 4th. And I'm going to stop there. R prime squared dr prime. You see, the whole problem is there's R prime squared. So let me take that in. And you will see which one creates infinity and which one doesn't. So that's equal to, well, 1 over 4 pi, 0 to pi, 0 to 2 pi, d theta prime, d phi prime. Now comes r to infinity. Let me multiply by this, and I would get a0 r prime dr prime plus b1 dr prime plus b2 over r prime dr prime plus b3 over r prime squared dr prime. Let's look at which one will have infinity and which one will not have infinity. So 1 over 4 pi, 0 to pi, d theta prime, 0 to 2 pi, d phi prime. This one, let me integrate. I would get a0 r prime squared over 2 going from r to infinity plus b1 r prime going from r to infinity plus so mind you, so this integral I'm approximating for r prime greater than r. We're restricting just to that domain to seek out problems. And you can see there are many problems over here. B2 times natural log of r prime from r to infinity plus, what is it, B3, r to the minus 2 becomes r to the minus 1, and I think by minus 1, r to infinity. Okay, we still have to do the theta phi integral, r to the minus 2, so it becomes r to the minus 1 divided by minus 1. Yeah. So 1 over 4 pi. I'm going to use a little bit of bad notation to compactify things, but you can precisely see where the infinity occurs. This one is bad. A0 times infinity, I don't need to do infinity squared over 2, it's still infinity, minus r squared over 2. So if A0 exists, this function cannot be integrated. Plus, same problem, infinity minus r plus b2, natural log of infinity minus natural log of r. And here we have, finally, 1 over infinity is 0 minus 1 over r. We still have to do theta and phi integral, but a0, b1, b2, and b3 are in fact functions of theta and phi. So you can see, if you want this integral to be finite, we better have a0 to be 0, b1 to be 0, b2 to be 0. Natural log of infinity is infinity, and b3 is just fine. So conclusion here is this function is integrable provided dr prime goes as some b3 over r prime cubed of this will be a function of theta and phi plus ie d falls off. It's typically phrased this way as 1 over r prime cubed. Only then the function is integrable. Okay, so we need one more fact before I state and prove Helmholtz's theorem. Suppose, well, this quantity, as you have seen, is in the integral, which looks like 1 over square root. Let me write this in Cartesian coordinate system. X minus x prime squared plus y minus y prime squared plus z minus z prime squared. Okay? So if I take a partial derivative with respect to x of 1 over the separation variable, this is quantity raised to minus 1/2. So I have minus 1/2 times the quantity raised to minus 3/2, which means it becomes minus 1/2 times x minus x prime squared plus y minus y prime squared plus z minus z prime squared. Oh, not square root, this is minus 1/2 minus 1 is 3/2 times the derivative of this with respect to x, so I get x minus x prime. Of course, these two cancel off. Okay, so let me. This is the final derivative. Now, the trick becomes handy. If instead of x, I take a derivative, because we'll be taking the gradient. If I can do it with respect to x, I can do it with respect to y and z. But now, let me take the derivative with respect to x prime of 1 over. Well, you will see that nothing changes, almost, except x minus x prime squared, y minus y prime squared, plus z minus z prime squared, 3/2. The 2's cancel. I have an x minus x prime. Now the derivative with respect to x prime, so there's a minus sign, and that minus sign comes out and kills this guy. The same is true for derivative with respect to x, y, and z. So in short, and here's a notation as well, I can write the derivative of this. Here, in that notation, I mean derivative with respect to gradient with respect to x, y, and z. That's the notation. That's equal to minus. Look, this one had a minus, this one doesn't. So this is the minus of that. But when you take gradient with respect to, or derivative with respect to x prime, y prime, and z prime. So I need a notation for that. And the notation is the following. I put a prime here. Actually, we just took 1 over the separation variable. You can have any function of the separation variable. This will hold true. So now, to be clear, gradient with respect to x prime, y prime, z prime. It's a simple fact. It's a quick fact. It's not very enlightening, but it becomes very handy. So I think we have put all the tools that we need for stating the Helmholtz theorem and a very quick proof. So before I state the theorem, it is such a useful result. It has its limitations. I want you to recall the 3 things we need. So when you have a function like u, and it's 4 pi, you'll see why it's there, but we don't need this. U of r to be a function of r prime, separation variable d tau prime. For this to be well defined in all space, d should, for large r, so for large r, or r prime, because we're integrating over the, should fall off as some constant, which is a function of theta and phi prime, but r prime cubed. That's when this integral can be defined. It could also be that d is only non-zero in a bounded region. That works, because they're far enough away, it's going to be 0. But at the very least, it should fall off as 1 over r cubed. If this doesn't work, we cannot directly apply the theorem. Maybe there are other versions, and we'll find some exceptions and even clever workarounds. But this time, if this exists, it's guaranteed to exist. The other fact that we talked about was just the derivative, but I'm trying to see if there was something else we needed. No, it is the fact that the gradient of 1 over the separation variable is equal to negative the gradient with respect to the prime variable. These are the 2 facts we need. Okay. So finally, the Helmholtz H-O-L-T-Z theorem. In simple words, if the divergence and the curl of a vector field is given to you, and if they vanish off nicely at infinity, then there's a way to reconstruct the vector field. Incredibly powerful. We'll have electric and magnetic fields, and if we know the divergence and the curl of the electric and magnetic fields, we'll have a formula to reconstruct the electric and magnetic field. And more importantly, when we try to develop equations for the electric and magnetic field, we know that when we have the divergence and the curl, we have enough information. From that, we can reconstruct the electric field. So it's a very powerful result. So if F is such that divergence of F is equal to D. Well, equal to D scalar. D just simply stands for divergence. And curl of F is equal to, well, C for curl. For known functions, or functions that are given to you, known functions D and C, such that D falls off as 1 over r cubed and C vectorially, so I should say C each component, Cx falls off as 1 over r cubed, Cy falls off, well, Cx, Cy, Cz. If this is the case, then here's a formula for F. And that's Helmholtz's theorem. F is given by negative gradient. The negative is not necessary. In physics, it comes in handy. But it comes in this form. It's negative the gradient of a scalar function plus the curl of a vector field W. Well, that's great. What are U and W? It's not very helpful if we don't tell you what it is. Well, there's an explicit formula. Then you will recognize the formula where U equals 1 over 4 pi D of R prime over R tau prime and W. So W is a vector. So this has to be a vector, C R prime that's the theorem. Okay, so we need to prove it. So proof. Just a quick note. The divergence of a curl of a function is 0. Divergence of the curl of a function equals 0. That implies the C cannot be any old function. Yeah, the divergence of C must be 0. This is not another assumption, but it's implied, it's contained, if C is in fact the curl of F, then the divergence of C must be 0. We're just noting that. Okay, the proof is very simple. I'm going to take the divergence of F and show that I will get D. I'm going to take the curl of F and I'm going to show that I get C. Let's do it. Divergence of F is equal to negative divergence of the gradient of U. I'm just taking the divergence of this side, plus the divergence of the curl of W. Well, that's already 0. And so, negative divergence of the gradient, or del squared, Laplacian, of U is, well, 1 over 4 pi. The Laplacian acting on x, y, and z. This D is a function of R prime. So it is really the Laplacian acting on this guy, d tau. Now you know why the 4 pi was included. del squared of 1 over the separation variable is nothing more than negative 4 pi delta cubed so this is the function evaluated at, so this is equal to 0 unless this is equal to 0 or r is equal to r prime. So therefore, negative del squared u is equal to minus 1 over 4 pi, and then I have a negative 4 pi integral d of r prime. This problem couldn't be easier. Delta cubed r minus r prime d tau prime. Well, the negative 4 pi's cancel, and you'll get the function evaluated at r, d of r. Well, that's what we wanted to show. The divergence of f is this, which is this, which is that. So, divergence of f is equal to this as needed. Oh, not done with the proof. We're done with 1/2 of the proof. So this property has been checked. The remaining property is fairly simple. There's a small twist, so let's twist. What am I going to do? I'm going to take the curl of f. So the curl of f is the curl of the gradient. Well, that is 0. This we know is already 0. Plus the curl of the curl of w. Back to vector identities in the inside cover of your textbook. This is nothing more than, well, let me continue here. Equal to this, I'm just using the inside cover, and you'll find that this is directly what you get. It's the gradient of the divergence of w. Well, this is exactly like the negative Laplacian of u. Nothing changes in the proof. Negative Laplacian of u was d. So the negative Laplacian of w is going to be c. Well, what we wanted was that del cross f equals c. We have shown that del cross f equals c plus stuff. So what I need to do is to show you that this goes to 0. As a matter of fact, I will show you that this goes to 0. We will now show that divergence of w equal to 0, thereby completing the proof. This is the theorem. Let's not forget what it is we're trying to prove. So, lack of space, I'm going to compute the divergence of w and then erase that. which I have to show, is 0. Divergence of W is equal to 1 over 4 pi. C is only a function of r prime, and then I get divergence of, so C dot 1 over d tau prime because the divergence is with respect to x, y, z variable, and this one is a function of x prime, y prime, z prime. So you guessed it, the whole trick about taking derivative with respect to x, y, z versus x prime, y prime, z prime. So what do? I put a prime here. But that's not the same thing. I know the derivative with respect to unprime is equal to the negative of the derivative with respect to prime. So I put a negative over here. Well, with this one, I can use divergence of 1 over this C of r prime is equal to the divergence of C times 1 over this plus C times C dot gradient of just a vector identity. You've seen this a million times before. What we have is this is the same as this guy. But this is divergence of C. This is 0. So I can replace this with that. And therefore, I have divergence of W is equal to minus 1 over 4 pi divergence of C over this d tau prime. This is r prime, and this is prime derivative. I have given up the unprime derivatives with a negative sign and replaced it with a prime derivative. Now you guess it, I'm going to use the divergence theorem. So this is 1 over 4 pi C of r prime, there's dA prime. This dA prime has an r squared in it for a sphere, if you do it in a spherical volume. This has 1 over r cubed, and this has 1 over r cubed. So I have 1 over r prime to the 4th, and then I have r prime squared. So as a result, well, let me make that very clear. Oh, let me also make that clear. This is over volume. This is over area. What area are we talking about? Well, I'm going to evaluate this over a sphere of radius r, and then I'm going to let r go to infinity. That's what I mean. So I integrate the divergence. This is over all space. Yeah? This integral is over all space. So what we have to do, the way r equals infinity, we cannot just do r equals infinity, we have to do the limit as r approaches infinity. So we do divergence theorem for a finite volume, and that takes it to the integral over the area of a sphere of radius r, and then we let r go to infinity. So let me explicitly put that in. I would get negative. And let me also say, not equal to, but for large R. So what am I doing here? I have a circle of radius R, and I'm integrating over here. So I would get C of R theta prime phi prime over, well, that is some constant vector, some C0, and over R cubed. We have decided that C falls off as 1 over R cubed. And there's another R over here, and then R squared sine theta prime, d theta prime, d phi prime. Remember, you're not integrating over R, you're integrating at a fixed R. And we're letting R go to infinity. Well, you can clearly see what's going on here. So that's equal to minus 1 over 4 pi. Let me write it out this way. R goes to infinity. I have R4, R squared. So I have 1 over R squared times some constant vector, R theta prime. You know, this constant vector comes from, for the scalar we had B over R cubed. Well, for a vector C, we have some constant B, but it has X component, Y component, Z component. So we're calling it constant C0. So it has some C value, CX value, CY value, and Z value. And all the R's have been brought outside. Sine theta prime, d theta prime, d phi prime. I don't care if it's 0 or anything finite. There's nothing, no limit over here. Sorry, this is no longer a function of R. It has been replaced. Yeah? Again, I want to be very clear. Remember, I wrote D for large to be B over R cubed. So C is a vector. So I have to say C0, some constant in the X direction, plus C0, some constant in the Y direction, plus C0Z in the Z direction over R cubed. And all of these guys can be functions of theta and phi. That's what I'm saying here. Well, this is just a number. It's 1 over R squared. You let R go to infinity, and you would get 0. That is all that was left to show. I had to show that the divergence of W was 0. Okay, so what's the most important feature here? If you have a vector field whose divergence and curl is known over the entire space R cubed, x, y, z, yeah, such that D and C, for very large values of R, they decay as 1 over R cubed. Then F is given by this formula. I can put another constant vector there. So up to a constant vector, I can put F0. Yeah? Because if I take divergence and curl of a constant vector, it is 0. So up to a constant vector, it's given by the gradient of a scalar and the curl of a vector field. And we would want the functions to fall off as 1 over R cubed. Otherwise, this formula, as part of where U and W was given by a certain formula, that integral may not be well defined. We will run into a case like that. But in that case, we'll have to use, it doesn't mean that this doesn't exist. It's not given by this formula. You have to find other clever means of finding F. Okay? Now, in physics, say you're computing the electric field. This is divergence of the electric field. That's proportional to the charge, for example. And if charge is contained in a certain region, you don't expect the entire universe to be filled with the charge in one of the problems we're doing. If that's the case, D is only non-zero in a small radius. Outside, it is 0. So this is not even being tested. Same thing with the curl. Curl, as it turns out, is for the magnetic field, and it's the current vector. Again, if you have currents in a loop, in a wire, in a star, and some charges around a star, it's still around a star. If you go a couple of light years away, there's no more current. It's exactly 0. If it's exactly 0, well, it's falling faster than 1 over r cubed. So this doesn't usually create a problem. So by and large, for physics, you can say that if you have a function whose divergence and curl is given to you, here's the formula for the vector field. The only problem is when you study cosmology, which is the science that describes the entire universe, when you have sort of uniformly charged, charge just smeared all over the universe, then these rules don't apply. So nothing of what we do really applies in cosmology in a very fundamental way. We'll have to tweak it. But that's a whole field of cosmology. We're not studying that. We're trying to do electrodynamics on Earth. And here, D and C are very contained objects. We have a nice formula. Good.